about Sir Harry. Harold Kroto was born in 1939 in Cambridgeshire, England. He graduated in chemistry at the University of Sheffield in 1961, and in 1964 received his PhD there. He then spent a few years doing research in the USA and Canada. He joined the University of Sussex in 1967, where he became a professor in 1985, and in 1990 he was made a Fellow of the Royal Society. During the 90s, he was awarded several international prizes and honours for his work. His research interests at Sussex have included spectroscopy of unstable species, carbon and metal clusters and microparticles, as well as interstellar molecules and surface-stellar dust. This is why I'm reading this. This work led to the discovery that very long carbon chain molecules are relatively abundant in interstellar space. During the project, which explored the possible source of these carbon chains in space, Sir Harry and his collaborators uncovered the existence of C60, which they named Buckminster fullerenes after the engineer Buckminster Fuller, who is noted for his geodesic design, similar in shape to the C60. Continuing research in Buckminster fullerenes led to the ultimate scientific accolade. In 1996, a Nobel Prize for Chemistry shared with Professors Robert Cohn and Richard Smalley of Rice University. During this time, Harry was also knighted by Queen Elizabeth for his services to chemistry. Well, so much for a brief introduction to Sir Harry, the renowned scientist. What I'd like to tell you about is when he first visited the UK in 1994. My husband Frank wanted the family to meet him, so we all went to dinner. The girls and I thinking we were in for an endless evening of sciencey shop talk. Well, it turns out that Harry's into graphic design. Turns out he knows lots about Pink Floyd. He even presents programs on the BBC. In fact, it turns out that Sir Harry is pretty well as multifaceted as Bucky is. I'd like to welcome Sir Harry Kroto.
Well, it's really an honor to be here, and thank you, Rosemary, to be back, to go from the UK, to go by British Airways, and United to the UK is quite interesting. It's still way out of time. I just want to say that the first time I met Frank, he was at the conference, I guess, and he introduced me, and he said, there's only one person I want to meet more than Harry, and that's Michelle Pfeiffer. So, it gives you an idea of the person. Fantastic guy, and in a sense, just like to say a couple of things about him. This is my favourite picture of him. I think the smile on his face says such a lot, what a charming guy he was. And in a sense, I guess, the one thing that he reminded me of was that whenever I was in his presence, if I ever had any worry, it disappeared. It doesn't matter what it was. He had this exuberant sort of personality that you completely forgot about what might have worried you. And there are only a small number of people like that. I can think of very few. So for me, it's a personal great loss, and for everybody else is very nice. But I think if you look at the newsletters from UK, from the NJ, there's this one which really sums it all up. Many of you who are not from Britain probably don't know one of the great sort of icons for kids of my age was Biggles and Bandits at 3 o'clock. And this is one of the books that we were brought up on. Has anybody how many people have read this book? They must be all British. But this guy could solve any problem, there's no doubt about it. And I guess deep in his heart and deep in the hearts of all kids who were brought up around the wartime, and Frank as well, I think we dreamed of being Biggles because he could solve all the problems. Bandits at 3 o'clock, and who were they? My PowerPoint is good, but I've not yet mastered Photoshop, so faces aren't quite the same. But this is the way I feel that we should be flying an airplane and one of these soccer camels. And this is a picture of us together, and then finally, this is our favourite. So basically, I thought Chop Us Away As You Know is the start of the conference. So I think this is it. It starts from now. What's the wrong say? When you get this prize, you end up being asked to pontificate. Okay? And so humbly, I'll leap into the pontification breach and say something about science that is to me. Science, in fact, everything is to me shapes and patterns. And for instance, chemistry is shapes and patterns too. And Newton invented classical mechanics to explain how the planets go around the sun. And basically, our picture of the solar system is not a lot different from our picture of electrons. And really, quantum mechanics was developed, and I believe it's the greatest intellectual advance of the 20th century. And there are only about maybe 2 or 3% of the population really know anything about it. The scientists who are aware of that. I mean, if you talk to anybody else, they wouldn't even think about quantum mechanics. They wouldn't even know about it. And one of my favourite lines is the enormous sign of lie in our Kleist matrices, and this is a sentence which somebody will certainly have read, but practically everyone knows that the components of total angular momentum of the molecule relative to X, Y, Z, fixed in space, have satisfied this commutation relationship. Well, at Kentucky Airport, I guarantee no one that I asked actually understood. But on the basis of that equation, we get angular momentum. It's the defining relation of angular momentum. This is quantized. So basically, there are numbers 0, 1, 2, 3, 4 associated. If I put them vertically like that, and think about orientations of the angular momentum, J has one orientation, and then there are lots of possible orientations. In fact, classically we have all these. But if you have J equal to 1, there are 3 orientations. And so, for the number 1, we get the orientation is 3. The orientation 0, we get 1. And for 2 is 5. So basically, the numbers 0, 1, 2 map onto the numbers 1, 3, 5. Now, the numbers are a bit complicated, even for scientists, so I'll put some boxes and make life easy for them. Then double them up with electrons, okay? And then put the boxes together, and then move them around. Then double there, another 2 there, another 5 there, and then move them around like this. And what have we got? We got the periodic table. Once you realise that basically the periodic table is a pattern based on the numbers 0, 1, 2, 3. And that's fantastic. And when I discovered that, or recognised that, I thought this was tremendous, because the periodic table really explains the whole of chemistry and essentially all the useful physics. I mean, all the rest is not really. Okay, so that's the situation. Oh, sorry about that, folks. We shouldn't go to see too much. You bring us down. We should have done that. But the underlying principles, really, the chemistry are very simple. And that's what science is all about. I've been thinking about chemistry itself. I don't know what it's like here, but I'm sure it's not a lot different from the UK. But the number of people going into chemistry is dropping very rapidly. And this is the molecule nitrosamethane. It's one of my favourite molecules. In fact, in some ways, it's my favourite molecule, because I look upon it like this. It reminds me of a dog that's been boozing. It's got a night out with Frank, actually. So it reminds me of. And the way that I think of it as a chemist is that it's a couple of carbons, 3 hydrogens, another carbon, 2 hydrogens at the front. So it's got 4 legs and a tail, nitrogen there, and a red nose because it's been drinking. And then from the rear, it looks like it's got the methyl group, and basically, because it's been drinking, it's sort of night on the tiles, and it sees the lamppost inside. It's an internal rotation. That's how I think chemists think about molecules. And it's difficult for non-scientists to really understand that. And as Madrid would say, ce n'est pas un molecule. Okay, with a bit of luck, you get out and go to the next thing. I'm not going to talk about the discovery of C60. Most people must be almost as sick of it as I am. There's a whole lot of fluorine chemistry, and many of you know quite a lot about that, so we'll not bother with that. But let's though go on to what links one's interest in science, but also there's a link between science and art, because Leonardo had drawn C60, and and called it icosahedron or oocosahedron abscissus graculus, the hollow structure. This is one of the earliest ones. And when I was on down in California, I found this fantastic sort of postcard. Some Californian artists also have been stimulated to think about this in a really rather imaginative way. And, well, pleasure to two of my colleagues here, Mauricio and Nicole from Sussex. We've really spent a lot of time over the last few years trying to make nanostructures, and I think they're very beautiful. In fact, this is I think perhaps the only useful material we found, and the use we found is that it's last year's Christmas card for the group. And aluminium oxide structures are very beautiful. So, in a sense, we as scientists can see the beauty of the nanoscale world. These are unaligned multiple-walled nanotubes. And in fact, we've seen these before because in this image we see it's actually a painting by Jackson Pollock. It will cost you about $1 million, but if you want ours, you can have it for only $100. So you can get something which I think in some ways is just as beautiful. Let's go back out to this and go on. Giant forms are not just C60, but larger ones. We'll talk about. I think a nice advance we've made just recently at Sussex, Mauricio, Nicole, and Juan, and Yan Chu, we've actually been able to put an insulating cover on nanotubes, which I think is rather nice. We've actually made nanoscale wires which are actually insulated. But it does seem, before I leave this, that this audience, perhaps as much as anything else, is aware there's a massive problem to actually bring to fruition the promise that nanotubes actually promise. We can make microgram quantities, but if we could make ton quantities of single-wall nanotubes in bundles of maybe 10 to the 18, we would really have a material which would revolutionize civil engineering and electronics technology. Mauricio's and Nicole's images here of priority carbon nanotubes, which was iron on the inside. I'm showing the pretty pictures because I want to try and span the science that we know with the arts as well. There's not only carbon nanotechnology, but there's also non-carbon nanotechnology, inorganic materials and things of that nature. Condensed phase, we've been able to produce these materials in the condensed phase as well. They're related to the geodesic domes, and that means there's a link with architecture, and the link with Mr. Fuller. His naming it after Mr. Fuller turns out to be a really rather nice thing, because he actually designed the nanotubes as well. I just go a little bit into a mechanism here, because the fundamental strategy that we have at Sussex is to try to understand how the nanotubes form. And there are two images, or two or three images, which I think show it best, because here we have a boron nitride nanotube, and if we look at the catalytic particle inside, we can see that there are the layers of the tube actually go into the particle. Maybe that's telling us something, that the carbon or the boron nitride sheets are actually being produced inside the particle. One of my favorite images is shown here, in which, in this segregation zone, there seems to be some really rather interesting activity going on, because it produces a three-wall nanotube. And the view I have is that what is going on is surface reconstruction on the surface of a carbide or a boron nitride alloy. In fact, if we think about it as surface reconstruction, as the carbon pops out, then maybe it comes out like that, and we find that we do see these igloo type structures which are coming out of these metal blocks. And then they stop when all the carbon is used. So I think this image is certainly one that I've rationalized and feel that it does indicate that some sort of surface reconstruction occurs on carbides. Okay, just before I leave this area of nanotechnology, I think one of the most amazing structures we've found is this. I think we've only found one of them. Jinping Yang and Tony Cheetham, who we've been working with at UCSB in the Materials Research Lab, they found this in our material. It's actually a triple helix which is being wound in situ. And this indicates that the next step on, if we can produce carbon nanotubes, maybe we can even produce them in situ, wind them by catalytic particles which actually produce a wound rope itself. The future, I see, chemistry hasn't even started. In fact, I thought I'd just show this. This gives you an idea of really, well, let's hope we can get there somehow, something disappeared. Try and go back. There we go. Because I think there's a view that chemistry is at an end. My view, it really hasn't even started, because if you look at the work of Max Perutz in 1950, he showed that the structure of hemoglobin was this. In fact, as the heme group takes on oxygen, the structure changes. These are the four heme groups as you see them. But looking at one, as oxygen goes on, the thing moves. We as chemists, first of all, can't make molecules like this without the help of biology. But biological systems made these millions of years ago. This is ATP synthase, a single molecule. The central rotor turns. This is it from the side. And this is the rotor at the bottom, which is actually changing, moving by proton transfer. In fact, this is the rotor, and it actually can turn. So it seems to me, looking down the center of the axis of this, and here again from the side, and this is the machine that produces all the ATP in your body. When you move your muscles, ATP is being used up. There's an electric motor which has been produced by biology, which actually physically produces it. Okay. I think the 21st century is exciting because the chemists of the future will think about making molecular machines in a way they haven't done before. We can only make simple molecules, but there are fantastic molecules to be produced in the future. Okay, so what are the problems? Why I think we're going to have bigger problems in the future than we have in the past. And the first one is the attitudes of science and the media. The second is the attitude of science of some responsible positions, such as politicians, and the attitude to science of students. Well, let's look at the media. That picture is one, but look at this. This is a picture in the local newspaper in Brighton when we discovered C60. Got into the newspaper. They couldn't be bothered to send a photographer, or they didn't have a photograph, so they picked a picture out of this usual sort of encyclopedic caricatures of a scientist. Okay? And a carbon copy of The Secret of Life, and in fact, I wrote, I put this up on the notice board, a student wrote fantastic likeness Harry. So I think it was probably the first show down here in the audience. But the point about it is, why do we have this particular image? And can we shake it off? Well, there's the picture. That's the typical one. Many of you know it's from E.T. Back to the Future. And the person responsible is this guy. And the point about it is, this guy's an imposter. People think that this is the fellow who created the beautiful theories of relativity, perhaps the most beautiful theory of the electron. The photoelectric effect is the simplest and the most elegant contribution. But in fact, this is not the guy who did it. I want you to all realize that this fellow is a true imposter. The guy that did it is this guy. And it's about time we and our kids realized it. And he looks a darn sight better than this guy, who I understand is a Scientologist, which I presume a large number of people think is a good thing to be. But anyway, I think it's about time our kids realize that it's the young who do the science. And in fact, the people who worked with us, Jim Heath and Sean O'Brien, were the young scientists who worked really hand in glove, and we worked together on the discovery of C60, you and you as well. And Jonathan Hare, shown here with the carbon arm. Another aspect of the newspaper where we discovered carbon chains in space, he said at the bottom, the chemicals were discovered thanks to Canadian work in radio astrology. That's what the media think we do. Okay, so that's one aspect of the problem. Well, some years ago I set up with a colleague at BBC the Vega Science Trust. And there's a website here, which I hope some of you will go to and look at what we're trying to do. And it's my belief that the first revolution in education was the printing press. Because up till that point, basically, books were written by monks, and the only book that you could get was the Bible. Okay. And that when the printing press came along, people could write books, they could be printed, and those who could read it. And they could be written not just in Latin, but in the language of the particular country. And then I'm sure someone said, you know, no one's going to read this book. Okay. They're not going to read that. Don't bother writing them. Let everybody be writing books and no one's going to read them. There's this guy, I guess I don't know, from St. Petersburg or Moscow, Fyodor. No one's going to read this book about these two brothers, okay? The point about it, the great books will continue, and they will be read, and the crack will have a certain height, and it will just stay at a certain level, and all the rubbish will go away. The internet, I believe, is the second revolution. And the reason is the first. You can make a program yourself, and you can post it on the internet, and you can broadcast it. And they will say, no one's going to look at it. But I believe the valuable programs, the valuable ones will be seen, and gradually will be spread. Okay, so that the quality and culture will be there. Of course, rubbish will be out there as well. The media are no longer in control of broadcasting. Up till now, the programs that you watch on the television are essentially totally controlled by the media, and they're controlled by advertising. You might say, well, the BBC isn't controlled by advertising. Not true. They have to compete and convince the government that they're competing with ITV, who are controlled. So they're controlled as well. That's the problem. If you're in a society which is sort of driven by making money and these things, you are driven by the lowest common denominator. So at last, the internet can be used as an advertising, as an education tool. MIT, I understand, I don't know what the number is, $100 million to post all their lectures on the web. The impact on that, on education, will be significant. I was in San Francisco last year, and I was watching a program on television from San Francisco City College. So I was watching this, and it was a fantastic lecture by this guy on Newtonian mechanics. It was a great lecture. I sat through it, and then at the end, this guy was at the University of Hawaii. Brilliant lectures, okay? The way in which universities will respond to the fact that we will now be able to see the top lecturers lecturing on major topics is going to be important. Chemistry and physics will be in a different situation because you still have to do some experimental work, okay? So, but there will be a change. Our aim is to develop internet and DV platforms for scientists and engineers to communicate directly, okay? Not through the medium of some media guy who understands no science. We've made programs, and one of them was a discussion programs on GM food, where we had a big pioneer new concept. We had a discussion between a group of people who understood the subject. They actually knew something about GM. On the ITV, one of the independent channels, there was a discussion about GM foods. The person in the chair was some newscaster, someone who reads the news. Everybody knew. There was a GM antagonist on one side and a GM protagonist on the other side. And they were set up because they knew they would just fight each other till death, you know. There was a guy from Christian Aid who was representing the third world who didn't know any science or GM. There was the accredited spokesperson from Greenpeace who started off by saying, I'm not a scientist and I don't know any genetics. Then there was a gentleman from the industry who was fairly quiet, okay, but did understand the subject. And there was a journalist who knew no genetics, but thought it was a good thing. It was a total disaster. We got nowhere. It taught us nothing. If we're going to have science understood by the public, we're going to have discussions by groups of people who really understand the pluses and minuses. And we've tried to do that. Now, I'm trying to sort of show you the sort of thing we've been working towards today. It's very, very hard work. It costs a hell of a lot of money. And it's bloody hard. Most of my time is trying to get money nowadays. It's not easy, for various reasons. A bit of luck, there we go. Okay, so let's look at a bit of the GM food debate. Give you an idea of what we're up to.
For thousands of years, people have been messing around with plants to try to make better food. It's called selective breeding, and it's absolutely the bedrock of agriculture. But it was essentially hit or miss. Hit or miss, that is, until the geneticists and the molecular biologists developed methods to put whatever genes they wanted to into whatever plants they chose. Genes that could improve their yield, could make them resistant to herbicides and pesticides, and to mean that less fertilizer might be used. So that all sounds marvellous. On the other hand, the criticisms of genetic modification would say that really it's science gone mad, tinkering with nature. The newspapers, magazines, even serious scientific journals are full of articles about Frankenstein foods. And at the moment, the British public, at least 2/3 of them, don't want it. Well, is that just because they don't know enough about the science? We've got 5 people here today who are going to help us to try and sort out that question. First of all, Angela Ryan, who's a molecular geneticist at the Open University. David Ho is a plant biochemist and a molecular biologist from Washington University in St. Louis, Missouri. Steve Jones, professor of genetics at University College London, certainly one of Britain's most visible geneticists. Janet Radcliffe-Richards, also from the Open University, is a philosopher of science who served on a number of committees concerned with the ethics of science. And finally, Dr. Mike Bevan, who is a molecular geneticist at the John Innes Centre at Norwich.
Now, what I want to do is just take you on that. There was a summing up and go to the second part of that program. And it was held at the Royal Society. It's cost me 40,000 quid. It was done together with the BBC. They didn't take it up, but it was taken up with the Open University, and the spin-off from this was 10 programs, discussion programs with the Open University. This program actually was posted on our website.
Let me just try and rehearse what I understand what some of the worries are. They are that the genes themselves that are put into plants might become toxic in their host plant, that they might encourage the plant to produce toxic or allergic substances, that they might even reawaken viruses or infectious agents that were dormant before, and that they could potentially spread, and that seems to be a major concern, spread to other plants and have a wide-ranging impact on the environment. Now, Mike, convince me that it couldn't potentially be dangerous.
Well, I think you're asking a very difficult question that can only be answered by extensive trials. And I want to convince you that these trials have been conducted in the case of herbicide-resistant soybeans, for example. These experiments, original experiments, were done 20 years ago. It's only now, after exhaustive tests on the agricultural performance of these plants, where key features such as stability of the transgene, the heritability of the transgene, and all sorts of toxicity studies that are published and are part of ours.
Now, that gives you a flavour of what we've been trying to do. Okay? The debate is a complex one. My view and the view of many is that GM is perhaps the most powerful technology that has been developed. The implications for society, ethical ones, are just enormous. And I think we're going to make very bad decisions in the future if we make those decisions without some understanding of what the issues are. Now, what I'd like to do is go back and go on to a little bit more. After that particular debate, it was seen by Lord Jenkin, who was the chairman of the House of Lords Select Committee on Science and Technology. He said, "I watched with complete fascination. It was by far the best discussion of the issues that I have seen or heard." We went on to make 10 programs with the Open University called The Next Big Thing. And these were shown after midnight on British television. In the Financial Times, It was said, the most enthralling program I saw on television last week. In fact, I've seen nothing so fascinating for months. Was called The Next Big Thing, Nanotechnology. It was a program on the subject of much of this particular conference. That was in the Financial Times. It indicates that we as a community can make programs and can make material, education material, that will be seen by major newspapers, and critics then will see this is interesting and this is important. The sort of program strands we've been making in our science discussions, like the one I've just shown you, scientific lectures by our top scientists. Most recent one, snapshots, we're now doing with the Open University. A day in the life of a young scientist. One thing that I want to do is a day in the life of a design engineer working with a Formula One racing team. On the Saturday, Michael Schumacher crashes and they say they've got a problem. Overnight they work, solve the problem, and Michael Schumacher can go to sleep behind the wheel and still win the race. Because it's about time people realized that the heroes behind the engineering, not just the guy who knows how to open a bottle of champagne and squirt it all over the place. Unless we do something like this, it's not a surprise that most of our kids want to be, I don't know, in Britain they want to be either David Beckham, who is equivalent to be a top basketball star over here, or Britney Spears. Are we surprised? No. Not surprised, because the culture, the background, heroes who actually make this world the way it is and save our kids from having to work 12 hours a day, 7 days a week just to survive. That's what science and technology has done. It's about time we as a community actually ensure that our children are brought up realizing that, and it's not the case. And then we're doing science workshops for young children. This is 8 and 9-year-olds. As time goes on, I think these are probably the most important things that we're doing. Well, if you click on Now Showing on our website, you'll get such things as this GM food debate, but also a lecture I gave at Berkeley 2 months ago. Berkeley have got all their freshman lectures on the web, and they have visiting speakers from NASA and other places. They're being recorded and they're available. I did a workshop at UCSB in Santa Barbara where we experimented with internet broadcasting. We did a little workshop with 8, 9, and 10-year-olds in the University of California, Santa Barbara, and it was broadcast to Guadalupe, 50 miles away, where the teacher got the full T connection so they could get this all sorted out, and we could then have a workshop like that. And later, I think Morinobu Endo is in the audience. We're going to try this with something like 3,000 kids in Japan. We already tried this last year using television broadcasting to 800 kids. So the universities, to get their act together, use the internet as an outreach tool so that the teachers who we all say, the problem is our teachers. Well, let's help the teachers get those interactions going. Help the teacher to get the science into the schools. The internet can do that. So it's each individual person. What we want to use is use the internet so you as an individual person can work out how to work with the local schools and get science out there. Vega team here. Chris Nielsen's got my laptop together. Jill Watson, who's the manager of the trust, and Jonathan Hare. Jonathan Hare now, they wanted me to be on one of these desert island programs. They wanted a Nobel Prize winner to look really stupid, right? And I thought, no way. But Jonathan spent a lot of time in electronics and also is a really physicist. He took my place and is the star of a program called Rough Science, which has become really very popular, where you put a bunch of scientists on a desert island. They've got to try and make a compass or a radio out of whatever's there. And the spin-off now is he's spending 3 months in the Caribbean, on a Caribbean island. Bloody hell. Okay. Let me go on to give you an idea. I want to show you one or two of our programs so that think yourself how the internet could be used. When Bill Klemperer, who I think is one of the most outstanding lecturers I've ever seen, came to the UK, I decided we ought to record him.
I've told you, and you have to believe that I tell you it's true, that carbon monoxide is the second most abundant molecule in the universe. And yet, our theory our equilibrium theory says there shouldn't be one molecule in the whole universe. It's that extreme. What does this say? Well, it doesn't say that thermodynamics is wrong. Of course it is. Right? And that's impossible to be wrong. It says that it's totally inapplicable to the chemistry of the everything is dynamic. That in a sense it very much resembles the Earth. If you ask what is the equilibrium status of everything, it's quiescent. Everyone's dead. That's it. And very uninteresting. So we would like something much more dynamic than the thermodynamic equilibrium. And I should say it's a testimony, really. Every time I mention to a group of college students, the audience breaks into tremendous applause as thermodynamics is not. And I wonder why. It might well be that it's so poorly taught that just the light that it doesn't.
Well, you see the normal mailer of chemistry. But the point is, to give you an idea of the problems, that I think within the spectroscopy community, Bill Klemperer is legendary as one of the great lecturers. Okay? There was no... I said to Bill, have you got a recording of you? So he sent me this terrible recording, I could hardly see it. So when he came to the UK, to the Royal Institution, I put together 14,000 quid to record that. That's what it cost to do a decent job. It was shown on British television. I went to Harvard, I said, we're going to make a program, we're going to give us some money. I got a letter which was basically a written 2 fingers. That's what it's like, trying to get the support to get our culture up there. And we've got to get to the people who've got some money to think we're losing some very important people who we haven't recorded. What would we give to have had, film of Faraday? What would we give for all these things? And for a good film of Einstein? Well, we're losing all that. And I think it's about time we realize that the technology is there to record this. I mean, there are other aspects of these. For instance, let me show you a pragmatic experiment again at the Royal Institution.
As you see the skull and the head go transparent, revealing the outside of the brain, perhaps you can get a sentiment of the power of the technique, because now we're visualizing those water molecules that have memory constants characteristic of brain rather than facial muscle tissue. Well, that resident skeptic may say, look, you could do that on the slab in a post-mortem room, but I'd like to hope I can be forgiven for not submitting myself to inconvenience at that particular experiment. Anyway, it's bad practice to teach graduate students to do experiments that they can't repeat several times.
Now, I want to show you something I think one of the best programs, most important programs we've made. Armand Lucas, a Belgian scientist, has, I think, produced the most outstanding educational concept, which will allow kids in school to understand how the structure of DNA was produced. And I'll show you this on here.
So we have a zig, the diffraction by the zig grating. Let's see what the zag grating is. Of course, you can guess if you incline the line in the other direction, you are going to incline this line in the other direction. So there you are.
There's no prizes for guessing that.
No prize for guessing that. It's just symmetry. Now let's put the zig and the zag together. Of course, you get a cross, a Morgan's cross. And so the diffraction pattern of a zigzag, if you had a polymer in the form of a zigzag, it has to be a cross. So the next picture is sine waves. And you can see that if you still have a beautiful Maltese cross. And remember that the sine wave is the projection of the DNA backbone on the plane parallel to its axis.
Now, if you come to our website, you get some further information on that. But with this slide, you can explain, just with a zigzag, how the diffraction happens, an optical transform, without any mathematics. Essentially, you can show kids how they can get the cross pattern of DNA. Now, to show you why it's important, if we go into BBC archives, what we can find is some very interesting film.
So what you'll get is a cross, like that, and the angle of the cross will depend on the angle of the helix. And when Jim went to King's with the erroneous structure line was falling in his pocket, he was familiar with his X-ray diffraction theory.
Morris read it in his usual way, didn't convey some enthusiasm. But I guess so yes, he didn't think Linus was the right structure. At the same time, however, he sort of let loose the bombshell, at least to me, was that actually there were two types of DNA X-ray photographs. The form which I knew about called the A form, which gave us crystalline matter, but there was a second form called the B form. Opened a drawer, took out a photograph, boy, I remember it was a perfect helix. It was a cross-like pattern, and he told me that it was repeated at 34 angstroms, and that it was a helix. So I said, Morris, you've got to have it out.
So, by knowing that, it adds so much more to the event, you know the science behind it. And I think that's an important aspect of the whole thing. Whilst I'm at it, I'll show you the guy who first actually took these X-ray pattern of DNA at King's College.
As a junior research student at the time, I was given the job of persuading a whole heap of Ransford to lie down in an orderly fashion and try and get an X-ray diffraction photograph of them. Not getting a very clear picture, I went to Morris Wilkins, who was looking at extracted DNA, and found that you could put it into fibers. So I used these fibers to make a specimen to give me a DNA pattern that I could compare with the Ransford pattern. Of course, pulling fibers isn't quite as easy as it sounds. You take some of the pure material and put a little on the microscope slide, add just enough water to make a gel, and then you can use that glass fiber stuck on the side of the microscope with a piece of plasticine, which you lower into the gel, and you need the lamp on the side to see the fibers, which when they come are very, very tiny indeed. It seems rather more difficult after 20 years than I, in fact, remembered.
That's the English approach to things going wrong. What I'd like to show you now was why we've got problems. Why we've got to work even harder than we've ever worked before.
Okay, welcome back. We're ready to resume our discussion of the 105th Congress. We're in your visit here for inauguration. And we're very pleased to have with us the Senate Majority Leader, Trent Lott of Mississippi, who can help us. Welcome. Thank you, Senator.
Good morning. I would like to know what advice would you give to a prospective student who is interested in following a career path similar to a senator?
Similar to a senator?
Yes.
Well, first of all, I would encourage you to take maximum advantage of your educational opportunities. We live in a great country. We have a great educational system that's not perfect. We spend an awful lot of money that doesn't always give us the results we want. But I can assure you, whatever you want to do in life, education will help you get it a faster start. For instance, when I was in high school and you were in the so-called pre-college curriculum, you had to take 4 years of science and 4 years of math. A waste of my time, a waste of the teacher's time, and a waste of space. No, I took physics. For what? Every physics teacher in America is out in the lynch me. Physics is great, and I think we need the best possible physics teachers and the best students in physics we can get. If you're going into physics or mathematics or science or medicine, but if you want to be a lawyer, you know that's where you're headed, maybe you'd be better off taking an economics course, a typing course, a computer course, or music, for heaven's sake, because it's good for the soul.
I think Trent Lott must have sent this black spot in the middle. Don't know how he did it. Now, I don't know what your response to that was, but I really was horrified. Even worse was the response of the kids, who applauded what he had to say. He was a major political figure telling them that they shouldn't learn anything about the intellectual culture in which our world revolves. I mean, basically, without science, engineering, and technology, they would be, as I say, back in the field or in the farms, in the mines. It's only 1830 Faraday went to the north of England to testify in a court case to try to get children under the age of 12 banned from working in coal mines, and girls. Until that time, kids 10 and 12 years old were working in coal mines. Not that long ago. And we know there are worrying aspects of the way kids are treated around the world. We've got a long way to go. And it's only science, engineering, and technology which has freed our kids and us to enjoy ourselves occasionally. And what do? We watch television with things like this, telling us that they're wasting their time. And I think that's very disturbing. So I think we've got to work even harder to try to ensure that this doesn't continue. Because if it does, I think we're not going to be able to solve the massive problems that will occur in the next century. Okay, let me just go out of that and on a little bit. One of the problems I see is language. And give you an example of language. In the Faraday meeting in 1954, the study of fast reactions, the German scientist Manfred Eigen asked Oxford Don Holly Bell how the English language would describe reactions which were faster than fast. Ronnie Bell replied, "Damn fast reactions, Manfred. If they get faster than that, the English language will not fail you. You can call them damn fast reactions indeed." Now, translating that is not easy. And, in a sense, here's another. A friend of mine, John Maynard Smith, sent a paper to a journal, a learned journal, in which he had this equation. And it was turned down. So he rang up and said, "What's the problem?" He said, "It's a bit complicated," the editor said. He said, "Do you need this equation? Di by dt equals a constant." He said, "Yeah, yes. He said, "Well, why do you simplify it by cross-multiplying the d's?" Little knowledge can be dangerous. I told this one then, I don't know, someone came out and said, "I'll tell you another one." There were two mathematicians in a restaurant, and they were discussing the ignorance of the general public with regard to calculus. Well, mathematics, but calculus in particular. And the other guy said, "No, it's not that bad. Some people will know some calculus." The other guy said, "No, $50 better. I'm going to go to the washroom. When I come back, we'll ask the first person we see the simplest possible problem in calculus, and I guarantee they won't know it." So he goes to the washroom, the guy calls the waitress over. The waitress says, "Yes," he says. Then my mate comes back from the washroom, immediately come over to the table, and he'll ask you a question. You won't understand it, but don't worry, because I'm going to tell you what the answer is. The answer is 1/3 x cubed. He said, "What?" 1/3 x cubed. 1/3 x cubed. 1/3. Say it again. Get it right. 1/3 x cubed. 1/3 x cubed. So she goes away. The guy comes back, drying his hands, sits down. The waitress comes over to the table, and they say, "We got a $50 bet on this one." He thinks he's got a winner here. So he asks her, "What's the integral of x squared?" She says, 1/3 x cubed. The guy can't believe it. He looks at her in amazement. The other guy thinks he's won his bet. And then she turns away. And then she looks back at the two of them in total disgust and says, "Plus a constant." Now, you should realize that in this audience, the large majority understand that. But by and large, 95, 98, 99% of the country won't understand. And if you want to understand culture, you have to understand humor, because it goes to the heart of it. And that's important for you to realize how few people really will understand that. Okay, why is it important? Well, senior nurses in the UK last year at a meeting, they were worried because quite a lot of nurses couldn't put the decimal point in the right place. This meant that if they were calculating the injection, you could get 10 times too much, or maybe 100 times too much, or 1,000 times too much, or 1,000 times too little. If Trent Lott had his way, we would have no nurses who would put the decimal point in the bankers, and he ought to be in hospital with such nurses. Indeed, a friend of mine was. He said, I was in bed, and there were two nurses behind me, and one asked the other how many milliliters there were in a microliter. He said, fortunately, she wasn't treating him. But those are the ways in which I think we can make people realize how important this is. Perhaps the most important graph I've ever seen is this one. It plots the proficiency in English of non-English speaking immigrants to the USA. And we notice after the age of 3 to 7, in some cases early as 3, some kids never become proficient in English. Now it's interesting that language is one of the things that you can quite easily determine. If you walk into a room and someone speaks to you, you know immediately whether they're fluent in English or not, or your own language, Japanese, or what it might be. There is almost nothing else that you can determine quite so quickly or so effectively. Now I suggested you think about the following, that almost any ability might follow a certain curve like this. It might be mathematical ability. It might be abstract ability. For instance, we have people coming up to Sussex in the first year who really cannot see handedness. They can't see the difference. They don't have an abstract perception of what is left-handed, the difference between left-handed and right-handed molecule. That's very interesting. Musical ability, analytical ability, other abilities, ability to manipulate things with our hands. If this is true, maybe not, but this may well be there. I always wondered what separated Enrico Fermi and Richard Feynman and von Neumann from me and many of us. There must have been something in their early life that made them fluent in mathematics. What was it? We should really try to find that out. So that's really why, in a sense, I've been looking at young children and thinking about workshops for those. These are the kids at UCSB, and these are Hispanic kids making C60, and they had a whale of a time. We can talk about, in fact, just to give you an idea of what I do with them, I actually talk a little about the story of the buckyball. I mean, it's a great line. Kids love the idea of buckyball. I talk about Einstein, and really that it was the young Einstein who did it, and that the students who work with us were young students. And that there's something to do with the football, and that there are pentagons on it, and that they can make these, get a feeling for it. Chemistry is very difficult because a bottle of benzene doesn't look a lot different from a bottle of water. But we as chemists, we can see the difference, and we've got to try to work out how to get them over that barrier. I like this kid. Really, really, really charming. This is around Macon. This is in the UK. Giant fullerenes, and they're really proud of what they do. And this is in Japan, the Mitsubishi Yokohama. Well, this is the only person in the world to find a use for C60. You need the kids to do that. We can teach them algebra as well. It turns out little kids have no difficulty with algebra. Okay? If you say algebra to a 15-year-old and 20-year-old, they might run through the door. And they can work this out. The number of faces on a cube is 6, the number of corners is 8, the number of edges is 12, and they can get the number 2. We can talk about the structure of the shell of a tortoise, and that there are hexagons and pentagons, and that they need the pentagon to close up. And that the size of C60 to a soccer ball is the same ratio as the soccer ball to the Earth. Important factors. And the local school in Angering is the first school in the world to make C60. Fantastic teacher there, Jan Meering. She got their kids making C60 when she heard how it had been done. And not only that, they linked it with sculpture and architecture. Not just to say, here's this molecule, but let's show that the same structures can occur on a macroscopic scale. You can link it with nature, okay, and Meccano. Now let me ask a question. Meccano had a copy that was copied in the US, and it was called Erectoset. How many had Erectoset in this audience? How many didn't have Erectoset? Wow, what a pity. pretty right. Well, let me tell you something about Meccano, which was the origin of this. Meccano was invented by a guy called Frank Hornby in about 1901. And Hornby double O and single O were electric trains. I had one of these, and it was absolute delight of my life. And this is the guy who invented Meccano. And if I did the same poll in the UK amongst engineers, I would have 100% of UK engineers have Meccano, 100%, and about 95% of scientists. That cannot be a statistic which does not have meaning. It has got to have some significance. Okay. And I was on a program on radio in the UK about a month ago called Desert Island Biz. And I talked about Meccano, and I said that the demise of British engineering and science followed exactly the demise of Meccano and the appearance of Lego. And this has created a stir. The king of Legoland said you're persona non grata in Denmark. All right? But the point about it is Lego does not teach you how to put nuts and bolts together. It does not give that facility with hands. It does not give an understanding of materials, of putting a bolt so tightly together that it stays together and not so tightly that you can't undo it, or making sure the threads match, or tearing the thread, all important abilities for our kids. Okay. Lego's taken over. And Lego's being replaced now because their sales are dropping apparently because the computer is coming in. We've got the kids now being played by computers. Okay? So you type your stuff into, and my name, Harold Kroto, is changed by Bill Gates to Harlot Crouton. Okay? That's the situation we face at the present time. This is where I spent a lot of my time with my nose glued to the window of this Bassett Lab in Manchester, with all these beautiful models and see the train on its own, and where Meccano was waiting to buy. In fact, here's an advertisement for Meccano. Meccano boys are keen, ambitious, and inventive. I better put girls as well in there. And here we see a totally different age. Advertising in the old days. And they see no boy who follows, or girl, who follows the Meccano hobby can be a bad boy. And so on. This is what it can make. And it could be a working machine. It could actually work. It could be underneath it. You could actually make it in materials which were close to the way that you build things. Okay. Someone even made C60. 1928, A.H. Findlay had counted down, you find this made out of Meccano. And it's bloody difficult to make it out of Lego, I'll tell you that. Science politicians, well, let's go on. Nearing the end, you want to finish. I finish with this. I like it because it's the way I feel, and I think many of us do. It says, I am an alien creature. I was sent from another planet with a message of goodwill from my people. The message says, Dear Earth people, when you finally at last destroy your planet and have no place to live, you can come and live with us. And we will teach you how to live in peace and harmony. And we will give you a coupon for 10% of all deep dish pizzas too. Sincerely, Bob. The reason for showing it is that obviously this guy is as concerned about the future as we all are. But he's also got a sense of humor. And I don't think we're going to get through the next century without both, because it's a lot of the people who are concerned just don't have any sense of humor at all, so they get pretty serious about it. And anyway, my last picture is this one, because I think that's what science can do. That's what C60 got this kid absolutely overjoyed. And I just love his face. But at this particular meeting, I thought I'd put these two together because I like both these faces and love them both. Okay. Thank you very much for being fantastic.
Well, true to form, another very thought-provoking talk by Harry. And for those of you who had the privilege of seeing Harry at past lectures, you'll recognize he's become as adept at PowerPoint as he was with those hundreds of overhead slides that he managed to shuffle through in a matter of seconds. As Harry mentioned about the race car driver, with a bottle of champagne spraying it over everybody, there was a lot of people behind in the pits there. And so it is with this conference. There are many people behind the scenes who have worked very hard to put this conference together. A surprising amount of work goes into these affairs, and during the week you will be introduced to many of them, but right now I need to introduce you to 4 of them, because they will be affecting your life over the next few days. And when you have problems or whatever it may be,